So I'm going to be talking about, it's too loud. Is it too loud? Yeah. Oh, even further? I drew a line. Even further? Okay. Is this fine? Can I start writing from here? Okay. So counting it's a very basic human activity. So we begin counting right from our school. We go learn 1, 2, 3. That's counting. Then as we grow older, we learn more and more refined ways of counting. So even in very early in school, we learn multiplication, how to multiply two numbers. Now that is also a form of counting. You're counting dots arranged in a rectangular fashion, say. So that's one form of counting. And even further, we learn about permutations, combinations. All of these are dealing with counting various kinds of configurations. So my talk is going to be, a lot of it is going to be around binomial coefficients, and you think of it as an application of binomial coefficients. So the other thing in my talk that's mentioned is something called Catalan numbers. As Sundar explained, Catalan numbers arise in the field of mathematics called free probability, but they also arise in various different contexts. There is a book, so the basic area of counting is called combinatorics. So there's a book on enumerative combinatorics by Stanley, in which there's an exercise, a very famous exercise, in which there are 66 different definitions for Catalan numbers. These Catalan numbers count a wide variety of objects arising in various fields of mathematics. So they are very ubiquitous in mathematics, and that's what I'm going to talk about. So I'll begin with 4 counting problems in which these arise. So the first one is called lattice paths. So that is just fancy terminology for the following. Consider the plane, and let's draw the lines x equals 1, 2, 3, so on, y equals 1, 2, okay. So here is the plane. Take one point, this is the origin, say, and take some other point in the plane. So for example, 1, 2, 3, 4, 5, 6. Let's take this point, 6, 3. So 2 points in the plane with integer, non-negative integer coordinates, and what we want to know is, we would like to get from 0, 0 to 6, 3. So we want to get from here to there, and we want to get to it in a certain fashion following certain rules. Each step we can take can be either up or to the right, and each step is exactly 1 unit in length. So we want to go up or right 1 unit in length and go from 0, 0 to 6, 3. So as you can see, there are many paths. So for example, one such path is this one. So you go up, twice right, once up, twice right, once up, twice right, and you reach the point 6, 3. There are many paths, and we would like to know how many such paths. This is a very basic problem. I am sure you have also seen this in your textbooks as an application of binomial coefficients. So in order to answer this question, we encode these paths. So we represent each of these paths just as I said, up, right, right, up. So encode each path by a string. So encode paths by strings. And these are strings involving only 2 letters, either up or right. You are not allowed to go down, you are not allowed to go to the left. You are only allowed to go up or to the right by 1 unit, by strings of U and R. So for example, this path that I have marked here, you are starting at 0, 0, going up 2 R's, 1 U, 2 R's, 1 U, 2 R's. So U, R, R, U, R, R. So it is encoded by this string of letters. So any path will be encoded by one such string. So we want to count, essentially counting the number of paths means counting these strings. Once you have the string, you also have the corresponding path by following what it says, URR, URR, URR. So essentially counting this or counting this, we have changed the counting problem to counting strings, which is a bit easier to do. So we would like to count those strings. Now we want to get from 0, 0 to 6, 3, which means you'll have to go finally, to go from here to there, you'll have to go up 3 units and to the right 6 units. This you'll have to do in some fashion or the other. So all your strings must have 3 U's and 6 R's. So these strings must have 3 U's and 6 R's. But there is no other restriction. If you take any string which has 3 U's and 6 R's, it will give you a path. So for example, if I take something like UU, RR, U, right? That has 3 U's and 6 R's. So it will give a path. Go twice up and then go completely here and then go there. It will give you a path. So essentially you are only counting strings of 6 U's and 3 R's. How many such strings are there? And that is a very easy question to answer. There are 9 positions, of which 3 positions must be U. Once you know where the U's are, the rest of them have to be R's. So the number of such strings is from 9 positions, you choose the 3 positions for the U's. So it is 9 choose 3, also written sometimes as 9C3. This is clear, right? And this is something that you probably have seen. This is there. I know it's there in the 11th and 12th standard books. Okay. So similarly, now 6-3 is nothing special, right? Similarly, the number of paths to Mn is 9 was the length, which is how many U's and R's together, that's M plus N, and out of which you'll have to choose M, whichever U's or R's. So it is M plus N, choose in this case it's N, which is also of course M plus N choose N. So this is the number of paths from 0, 0 to any point, right, where M and N are non-negative. That is, the point has to be in the first quadrant point. Okay. Now we want to make, this problem is too simple. This is not what I want to talk about. What I want to talk about is a slightly more interesting problem where we put further restrictions on the path. Okay. So now the further restriction that we would like to put is the following. So I'll erase this and redraw it with different points and explain the restriction. So now let us say we want to go from 0, 0 to say the point 4, 4. Right? We want to go from 0, 0 to 4, 4. We know the number of ways of doing that is 8 choose 4, right? M plus N is 8 and M or N are both 4, so 8 choose 4. Number of paths is 8 choose 4, but we would like to look only at those paths that stay on or above the diagonal, this diagonal. So there's the diagonal. So we want paths, how many paths stay on or above the diagonal. Now this is a more interesting question. And not so simple to calculate. It's not clear how you would calculate this figure. How would you calculate this number of paths that stay on or above the diagonal? For example, here is a path. So that is a path. You are allowed to touch the diagonal. You are not allowed to come below it, right? It has to be on. It can be on. The point can be on the diagonal, or it can be above the diagonal. But you should never reach at this point or this point or this point or that point. You should not go to a point below the diagonal. Okay. So this is one counting problem. This is one counting problem that I would like to describe. How many paths? So these are paths from 0, 0 to the point n. Here n is 4, but you can take n to be anything. So let me just do the case where n is 3, right? When n is 3, let me list out all these paths. So if n is 3, we see that there are the following paths. So what are the paths? So either you can go one all up and then all right, that's completely above, or you could go 2 up, right, right, that's one, or you could go 2 up, right, up, right, or you could go 2 up. Okay, no, that's not allowed. So we want to reach this point, so you could go 1, 1, 2, 2, or 1, 1, 1, 1, 1, 1. And that's all. You can try. You will only see these are the only 5 ways of going from 0, 0 to 3, 3 along a path which lies completely above the diagonal. Although the number of paths, of course, is 6 choose 3, that's 15 paths. There are 15 paths totally, but of which 10 of them will violate the condition and they will go below the diagonal. Only 5 of them do not violate this condition. So the number for n equal to 3 is 5. So when n is 3, the number of paths is 5. So let me also do n equal to 2. It's an easier one. When n equal to 2, either you do this or you do this. There are only 2 paths. When n equal to 1, of course, there is only 1 path. So you get a certain sequence of numbers beginning this way. For every n, you will get a certain number here, and they form some certain sequence 1, 2, 5, something, so on. And that something happens to be, if you do it carefully, for n equal to 4, you will see that there are 14 paths. So the sequence begins with 1, 2, 5, 14, etc. Now this is the sequence that I would like to talk about. So this is one example of a counting problem and a certain sequence of numbers which arises from this counting problem. Now let me shift gear. Let me go to another problem. Okay, so second problem is triangulations of an n plus 2 gun. So take a regular polygon with n plus 2 sides, right? And we would like to divide this into triangles by drawing diagonals. You do not allow the diagonals to intersect. So there is an element of something being non-crossing comes in here. You don't allow the diagonals to intersect, and you would like to divide this n plus 2 gun into triangles. So for example, again, let me begin, say n is 3. So n plus 2 is 5. So we are talking about a pentagon here. So I want to take a pentagon and divide it into triangles by drawing diagonals, cut it up into triangles. So here. Now I label the, which way shall I do it? So I label, let me begin with this as 1. I label the vertices as 1, 2, 3, 4, 5. In general, 1 up to n plus 2 will label the vertices of that n plus 2 gun, and I want to divide this into triangles. So how can I divide this into triangles? One way I could do is, I could draw this diagonal and I could draw this diagonal. Now we see that the pentagon has got cut up into 3 triangles. But there are other ways of doing it. Obviously, if I have this way of doing it, I can rotate this picture and get another way, which is this one. But again, the numbering remains the same. It's only the inside that is rotated. So I have at least 5 ways of doing it. And fifth way is so here are 5 ways of cutting that pentagon into triangles, and one can see if you try doing this, there are no more ways. Again, you get 5 ways. When n equal to 3, there are 5 ways. Here when n equal to 3, there were 5 paths. So let's see when n equal to 2. If n equal to 2, n plus 2 is 4, so now we are thinking of a square. And clearly there are 2 ways, either you draw this diagonal or you draw the other diagonal. When n equal to 2, there are 2 ways, and here also when n equal to 2, there are 2 paths. Right? And again one checks when n equal to, if you go to a hexagon and try all possible ways of cutting it, you will see that there are 14 ways of doing it. So that sequence somehow seems to agree with this sequence 1, 2, 5, 14. Of course, when n is 1, you have a triangle. You don't need to draw any diagonal, there is only one way, it is already a triangle. So you have 1, 2, 5, 14 arising in this context. You also have 1, 2, 5, 14 arising in this context, triangulations of a n plus 2 gun. Okay, so that is 2 problems in which this sequence arises. Let me describe one more. And this is where this non-crossing partitions which Sundar mentioned comes in. So third one is, so let's call this the handshake problem. Okay, so you're given 2n people sitting around a circular table. So given 2n people sitting around a circular table. So again, I'll take n equal to 3 and work it out, and then we'll see what happens. So here's my circular table. And here are my 2n people. Sitting around that table. Now what these people would like to do is to shake hands with each other. So this one may like to shake hands with 3, 4 may like to shake hands with 6, and 2 may like to shake hands with 5, right? One might like to do that. But we were only interested in configurations where the hands don't cross. Now that's not valid. If one wants to shake hands with 3, then 2 will have to shake hands crossing the shaken hands of 1 and 3. So we want to avoid that situation. So we want to consider handshakes where there are no crossings. Hands should not cross. And let's see how many ways there are. So maybe 1 could shake hands with 2, 3 could shake hands with 4, and 5 could shake hands with 6. That is one configuration. And there are others. Maybe 1 shakes hands with 2, 3 with 6, and 4 with 5. That's one configuration. or then maybe 1 shakes hand 4, 2 with 3, 5 with 6, or maybe 1 with 6, 2 with 3, and 4 with 5. Or finally 1 with 6, 2 with 5, and 3 with 4. And these are all. These are the only ways in which the problem, as I stated, can be solved. If people have to shake hands in pairs, right, and in such a way that hands do not cross, there are only these 5 solutions possible. Again, note that there are 5. Once again, you can do this problem when n equal to 2, when n equal to 3, when n equal to 4. That means 4 people sitting, or 6 people, or 8 people. Of course, there have to be an even number of people, because otherwise somebody will be unmatched, right? So everybody wants to shake hands. There have to be an even number of people. So with 6 people, you get 5. With 8 people, you'll see you'll get 14, and so on, right? Again, this agrees with that sequence. The same sequence of numbers occurs in so many contexts. Let me tell you one more context in which it occurs. So in the first talk today, where a group was defined, one of the laws that a group operation has to satisfy is that it's associative. So let us look at this associativity a little closer. So this is the fourth. Parenthesizing an expression with n plus 1 terms. Okay, in this, rather than beginning with 3, I'll begin with n equal to 2 first and see what happens. You have, when n equal to 2, three terms, say A, B, C. So you have 3 terms A, B, C, and you would like to multiply these. Now there are many ways in which you can insert parentheses. Not many, in this case there are only 2 ways. Either you could multiply A and B first, then multiply the answer with C, or you could first multiply B and C and multiply A with the result of that. So there are 2 ways in which A, B, and C can be multiplied in that order. Of course, there are many other ways in which you can multiply if you are allowed to interchange the positions of A, B, and C. I do not allow that. A, B, and C have to be in that order. You are only allowed to change how you are going to perform this operation of multiplication, in which order, but not changing the order of the terms A, B, and C. A, B, and C have to appear in this order. When n equal to 3, 4 terms A, B, C, D. So now you have 4 terms which you want to multiply together. How many ways can you do this? 2 at a time. You are only allowed to do multiplications 2 at a time. You have to take 2 things, multiply. Then you can take the result and multiply with something else. But you have to do it 2 at a time. So there are many ways. So for example, you could first multiply A and B, then multiply the result with C, and then multiply that result with D. So this is one way of doing it. Or you could multiply A and B. You could also multiply C and D, and then multiply those 2. Or you could take A, multiply with the product of B and C, multiply that with D. Or you could take the product of B and C, multiply that with D, then multiply with A. Or finally, you could do it in the other order, A with B, C, D. And again, remarkably, there are 5 ways of doing it. When there are n plus 1 terms, 3 plus 1 terms, there are 5 ways. N is 3, there are 5 ways in which you can multiply. Once again, you can do this calculation when n equal to 2, there are 2 ways, when n equal to 3, there are 5 ways, when n equal to 4, which means A, B, C, D, E. If you check, if you write down all possible ways of doing it, you count, there will be 14 ways of doing it. So this sequence arises very strangely in all of these problems which don't seem at first sight to have anything to do with each other. Okay, so let me state the result. I'm not going to prove much. I'll just give you indications of how these things are done. Have identical solutions. That's one part of it. And the solution is given by so in each of these problems there is a parameter n, right? In the first problem n represented, nn was the point. In the second problem, or in this problem, n plus 1 is the number of terms. In the triangulation problem, n plus 2 was the number of sides of that polygon. There is always a parameter n. So the solution is given by Cn, and this number has the following formula. The formula for Cn is 1 over n plus 1, 2n choose n. You can tabulate this for the first few values of n and see. If you tabulate this for the first few values of n, so n, Cn. So when n is 1, it's 1, 2. 1 over 3, 4 choose 2. 4 choose 2 is 6, 1 over 3, 4 choose 2 is 2. And when n is 3, 1 over 4, 6 choose 3, is it? Yeah, 6 choose 3 is 20, and 1 over 4, 6 choose 3 is 5, 14. When n equal to 5, it turns out to be 42. You get this sequence. This sequence is exactly the common solution to all of these problems, right? That is what this theorem is saying. All these problems have a common solution, that's part 1, and this solution is given by this figure. So I'm not going to prove this, but I'll do parts of it. So what I will try to show is, I'll try to show that the path problem, first problem that we took, the number of paths which stay on or above the diagonal is exactly given by this number Cn. So it will show that the first problem's solution is given by this, right? As for the others, I will indicate how you can transform some of these problems into some other problems, and therefore we can deduce that the number of solutions is the same. Okay, so but before I get to doing that, first notice that it is not even clear that Cn is an integer. It's not obvious that n plus 1 divides 2n choose n, right? 2n choose n is the middle binomial coefficient in that nth row, right? It's not even clear that n plus 1 always divides that, but it does. And that's not too hard to show. However, this is easy. Because we can rewrite this as 1 over n plus 1, 2n choose n, as the difference of two binomial coefficients. It is 2n choose n minus 2n choose n minus 1 psi. And why is this? This is easy to prove. If you just use the formula for what n choose k means, 2n choose n is 2n factorial by n factorial squared. 2n choose n minus 1 is 2n factorial by n minus 1 factorial into n plus 1 factorial. Then pull out common factors, simplify, you will exactly get this side. This is easy to see, and therefore it shows that this number, which doesn't look, which is not clear, it's an integer at first, since it's the difference of two binomial coefficients, both these being integers, that is also an integer. Okay, so that's fine. So it's an integer, that's good. But why is the solution given by Cn for the path problem? Now that uses a very pretty trick called the reflection trick. So let me explain that. And in that reflection trick, very naturally you will see that this is the answer to the counting, path counting. Okay, so what are we trying to count? We are trying to count all paths from 0, 0 up to the point n, and we are trying to count those paths which stay on or above the diagonal. So if you want to count that, a natural way of doing that would be take all paths first of all and then remove those that violate your condition, right? So reflection trick says, so count of paths lying, I'll just say above, I mean on or above, right? Lying above diagonal equals number of all paths minus the number of violating paths. Violating paths means going below the diagonal at some place or the other. All paths, what all paths? All paths from 0, 0 to n, of course. That count we know. We know the number of paths from 0, 0 to n, all paths which go only up or right. We know how to do that. That number is exactly 2n choose n. This part is fine. So all we have to do is to show that the number of paths that violate that condition is 2n choose n minus 1. So to finish the proof, we need to see that the number of violating paths is exactly given by 2n choose n minus 1. And here is where the reflection trick comes in. So it goes this way. What we do is we consider a path which violates the condition. So if it violates that condition, there is a first point at which that condition is violated. So we look at that point closely and do something there. Okay, so I'll do it by example. Consider a violating path. For instance, okay, so here is the point 0, 0. I'll take n to be 5. Here is the point 5, 5. And here's the diagonal. Oh, sorry. So which point did I actually take there? I should have taken, I took 4, 5, so I have to take 5, 5, which is here. Then draw the diagonal. And I'll take a path which is violates the condition, which goes below the diagonal. A path from 0, 0 to 5, 5, which at some point goes below the diagonal. For example, maybe I go up and then go below the diagonal here and then do whatever. Maybe I go below the diagonal again. Some path. Maybe I should do that in a different color. Here is my path that violates the condition. So what I want to do is I look at the point at which the condition is first violated. So I go along the path. This point is okay. This point is okay. But this point is not. This point has come below the diagonal. So I mark this point. And there I draw a line which is parallel to the y equals x line. So I draw this line. Then I reflect the rest of the path around this line. Rest of the path is going to be reflected around this line. So let me draw this fully because I need it. So, and the reflection of the path, I will draw maybe in one more color. Up to here, it's the same as the original path. From here, I start reflecting this entire path in this line. So, what will I get? The reflection of this part is this. The reflection of this part is this. The reflection of this part is this. And the reflection of this part is this. So, finally, I end up at some point. Now, let's see. Let's analyze this a bit more closely. So, consider a violating path. So, reflect along a line parallel to y equals x, passing the first violating point. So, now we get a new path. This new path still begins at the point 0, 0, right? The new path still begins at the point 0, 0. However, the ending point has changed. The ending point originally was the point, this was n. Now it becomes, in this case 5, 5. So, it has now become n plus 1, n minus 1. Note that this will always happen. Always the ending point will be n plus 1, n minus 1, because the line of reflection is always going to be this line, because the first point at which you violate will be either this or this or this or this. It's always on that line, right? Or this, or the very first one here. The line of reflection is going to be always this blue line. So, whichever path, violating path you take, the line of reflection is always this, and when you reflect n around this line, clearly you get to the point n plus 1, n minus 1. So, we get a new path that begins at 0, 0 and ends at n plus 1, n minus 1. Okay, good. So, we have this new path. Now, I am saying that what I would like to assert is that the number of violating paths is exactly the same as the number of paths that begin at 0, 0, end at n plus 1, n minus 1. So, this is the main claim which has to be understood. So, number of violating paths, I claim, equals number of paths from 0, 0 to n plus 1, n minus 1. So, let us try to understand the justification for this claim. This claim is the most important claim in this whole proof. So, why is this? Why is this? What I am trying to say is, if I take any path at all from 0, 0 to n plus 1, n minus 1, it is obtained by this procedure of taking some path from here to there which violates, and then reflecting around the first violating point, reflecting around that line passing through the first violating point. This is the claim that we have to understand. Okay, so let us see why. So, this is because this procedure is entirely reversible. So, this is because the procedure is entirely reversible. So, let us see that. So, what do I mean by that? So, let me take this picture. And one. So, let me take this path. This is some path from 0, 0 up to the point whatever, n plus 1, n minus 1, this is 5, 5 for us, 6, 4. So, some path to 6, 4. Now what you have to notice is that the point 64 lies below the diagonal. So note that .64 lies below the diagonal. Sorry?
Below the blue line.
Yeah, below below the diagonal. Oh, sorry, yeah, below the blue lines, correct, yeah, thanks. Yeah. So the point 64 lies below the blue line. That is the point n plus 1, n minus 1 will always lie below that line. So once we observe that, it follows that there will be some point thus below the blue line. So there will be some point at which the blue line is crossed. Since 0, 0 lies above and this ending point lies below, this path has to cross it at some point. Once you know it crosses it at some point, you can reflect. You can take the point at which it crosses and reflect the rest of this path above, about that same line. So we can reflect as before. To get a violating path. To NN. So reflect this and you get back your original path exactly. So if you reflect it from here, so this will go this way, this way, this way, this way. And that was the original path, right? The original path went 1, 2, 2, 2, 2, 1. That's exactly that path. So this procedure is entirely reversible in all cases. This is an example I did, but one has to justify a little bit more carefully that this procedure, essentially it's the same proof, right? This procedure is always reversible and will always give you a violating path. So in some way I have matched up the set of all violating paths with the set of all paths from 0, 0 to n plus 1, n minus 1, and that is the key thing. I have matched it up with the set of all paths from n plus 1, from 0, 0 to n plus 1, n minus 1. That is something that we know how to count. We know how to count all paths from 0, 0 to anywhere. So this number therefore is 2n choose n plus 1 or 2n choose n minus 1, and so we are done. Since since the number of good paths equals number of all paths minus the number of violating paths, and number of all paths we already know is 2n choose n, and the number of violating paths is the same as the number of paths from 0, 0 to here, which is the sum of this 2n choose any one of them n plus 1, 2n choose n plus 1. And this number is exactly what we call the Catalan numbers here. By the way, Catalan numbers are named after the Belgian mathematician Catalan, but they have been known, according to at least from what I read up on Wikipedia, they have been known much earlier. Euler knew it, and it was even known to in ancient China apparently. Okay. So this proves at least one part of the theorem I said. Two parts of the theorem I said was all these problems essentially have the same solution. That was one thing, and I said the solution is given by this formula. So I proved that the solution to the first problem is given by this formula. Now what about the rest? So to deal with the rest, I am not going to be able to do it fully, but let me give you some ideas. So here is one step in dealing the rest. So question I would like to answer is, how is, yeah, is it, oh, that, which one is right, I'm not sure, okay, it's, sorry, yeah, okay, in that case let me just end with the, maybe I won't discuss this, but let me just say one interesting problem. So question. So this sequence of Catalan numbers that you have, you can form matrices from them. So here is the sequence. So 1, 1, 2, 5, 14, 42. This is the sequence. You form a matrix by just one, 1, 2, shift. Next matrix 1, 1, 2, 1, 2, 5, 2, 5, 14. The first 3, the next 3, the next 3. In this way you form a whole set of matrices. And the problem is, all these matrices have determinant 1. It's quite amazing. You calculate the determinant of any of these matrices, all of these have determinant 1. And in fact, that's almost a characterization of that sequence uniquely, provided you set the first 2 to be 1, and then if you have any sequence which satisfies this condition, it must be only this Catalan sequence. Okay, sorry, thank you. I want to make one more comment. See, there is also this website called OIES, Online OEIS, Online Encyclopedia of Integer Sequences. In this website, if you have a sequence of numbers and you want to find out what kind of sequence is it, where does it fit in, you just enter the first few terms of your sequence and it will give you various choices about where these numbers have arisen before in mathematics. It's a very interesting thing. If you're calculating, counting various kinds of things and you don't know the formula for something, that's a very nice place to find out these formulas.
The last year I give to whom?